Let us now discuss the shunt regulator circuit. So let us draw the input unregulated voltage Vi. It contains a series component here and a shunt component here. It's a Zener diode and the load. So this is the structure of a shunt regulator. The hero of this is this Zener diode. This is Vi, the unregulated Vi. We'll call this as Rs. This is Vz, and this is the load resistance R0, and you have V0, and V0 is equal to Vz. So if I name this as Is or In, and this is Iz and I0. So these are the various parameters in a shunt regulator. How does the regulation happen? Basically, Vz is a reference Zener. The voltage across the Zener is constant and it tries to maintain V0 constant in spite of the fluctuations in Vi or fluctuations in R0. Let us see how the operation how the regulation operation functions. Now look at the Kirchhoff's current law here. At this node, you have In, Iz, I0. In is equal to Iz plus I0. Iz plus I0. And this is the core equation which performs the regulation. Now Vi can vary from a Vi minimum value to a Vi maximum value, and R0 is not under our control, again can vary from R0 minimum value to R0 max value. And as a consequence, when R0 is minimum, I0 is maximum, and R0 is max, I0 is minimum. The operation of the shunt regulator hinges on this device, which is the Zener diode. Let us try to understand the characteristics of the Zener diode, static characteristics of Zener diode, and how it affects the regulation performance here. So let me draw the IV characteristics. This is the V, this is the I, and let me take only the reverse characteristic, the Zener's reverse characteristic, which will be something like this, where this line intercept will be Vz on the voltage. So now this In here, the current is given by Vi minus, this is Vz point, this potential here is Vz at this node, Vi minus Vz divided by Rs. So this is the current that flows in through here, and this current is independent of the value of R0 or value of I0. So depending upon the value of R0, there is commutation between I0 and Iz to maintain In fixed to this value. So the current through the Zener has flexibility. It can operate from a max value Iz max to a min value Iz min. And this in fact gives you the regulation. If suppose I0 is 0, then the whole of the In current flows into Iz, so the operating point will be somewhere here. If I0 is a maximum value, then Iz will decrease and it will probably be sitting at min value. The operating point will be here. So it is Iz here that actually is adjusting its value. The regulation happens because of the capability of the Zener to take varying currents through it at a constant voltage. The Zener current can vary from Iz min to Iz max depending upon the value of the load. Consider now few operational cases. Let us say case 1. Now here Vi is at its max value, Vi max, and let us say I0 is 0, which means it is open circuited. Then the entire IN current flows through the Zener. So IZ will be equal to IN because I0 is 0, and that is Vi max minus Vz divided by Rs. Now this is the max value of the current that can flow into the Zener in the circuit. So it will get, this will be the operating point, it will get positioned here. And that will be Iz max for the circuit. And see to it that it is less than or equal to Pz by Vz. Pz is the Zener's power rating. So when you go and choose select a Zener, it will have a power rating in the data sheet. So you will have a 1 watt Zener, you have 400 milliwatt Zener. So whatever that power rating divided by Vz, Zener's Vz, will be the limiting or the max permissible value of Iz. So this Iz value which you calculate here should be less than that, so that the Zener doesn't blow. The second case, the second limiting case happens when Vi is Vi min and I0 is maximum. That is when R0 is at a minimum value. So you have I0 max. So under this condition, this I0 plus Iz should be equal to In. There should be at least a minimum value of Iz to pass through the Zener in order that the Zener provides a constant voltage Vz. So therefore, Iz minimum at least should flow through this. So Iz should be set at Iz min as the operating point. So we know that Iz min now plus I0 max should be equal to In, and In under this case is Vi min minus Vz divided by Rs. So this is another limiting case where the operating point as far as the Zener is concerned is here. So these two limiting cases will actually determine what should be the value of Rs that you have to choose. It will become clear if we work out an example. Let us now see what is the efficiency of this circuit. Efficiency is defined as the output power divided by the input power Pi. Output power, which is V0 I0, input power Vi In. So we can write it down as V0 I0 by Vi In. Let us express in terms of input voltage and output voltage. So we have V0 I0 by Vi into In is Vi minus V0 by Rs, Vi minus V0 by Rs, and let us define another term delta VIO, which is Vi minus V0. It is called the input output voltage differential, Vi minus V0, which is the input output voltage differential. So now therefore we can rewrite efficiency as V0 I0 Rs divided by Vi into delta VIO. So this will be the efficiency relationship. Observe that as delta VIO, input output voltage differential, increases, efficiency will decrease, which basically means that if I am having a linear shunt regulator, let us say with input output differential as some voltage, for example, if I take Vi of 10 volts, V naught of 5 volts, input output differential would be 10 minus 5, 5 volts. For the same phi, if I am having Vi of 15 volts, then the input output differential would be 10. So the 15 volt input would have a lower efficiency than the 10 volt input linear regulator. So V naught I naught is nothing but P naught, which can be obtained from the spec. RS is calculated by design. Vi is given from the input spec. Delta VIO is also an input spec, and from here we can calculate the efficiency of the circuit. So the important thing to note here is the input output differential voltage. Higher it is, lower the efficiency.